Yeah. So okay. So these are like the content of my talk. So I'll start with the motivation of the problem, and then mathematical formulation. So I'll try to discuss some basics on this formulation part, and then we'll discuss some few results, and then I'll conclude my talk. Okay. Okay, so the motivation behind the work. So so I've used word the flow around a non-flat object. So it's basically motivated by the coating flows, so or coating of discrete objects. So in many industrial process, right, we can see the we do coating of non-flat objects. So non-flat objects. So here I've taken examples from health industry. Okay, so I've taken this two examples. This one is the stent, and this one is the contact lens. Okay, so the stent, right? Stent is like it's a wired tube actually. So we use stent to remove the blockage in our arteries. So stent is initially it's in the flat position, like it's a balloon kind of thing actually, and so it's made of metallic wire. Okay, so initially it's in the flat position. Okay, so let's say, and just draw some pictures here. Okay, so yeah. So uh, okay, I don't see cursor here, sorry. Okay. Is a OneNote visible, Dr. Vora?
Yes, sir. Yes, sir. We have a screen, sir. Yes, sir.
So let's say this is our artery, right? Let's say we have some blockage here. Right, let's say this kind of blockage is there. Okay, so we insert a stent here, right? So after, so it's, as I said, stent is like it's a metallic, a tube of metallic wire, made of metallic wire. So when I put a stent here, right, initially it will be in a flat state, and it will be like this. If you inflate it, so it's like you're, by putting this stent on your arteries, inside the arteries, you can remove the blockage, and you can later on you can remove this balloon. So we do this by an angioplasty procedure, right? So that is the stent. So as I said, the stent is it's a metallic wire, right? So we have a coating of expensive drug on that wire, right? And second example I've taken of contact lens. Again, in contact lens also we have some coatings, right? So the coating of these objects, or the things, I mean small things, right? It's not very clear. I mean either we use coating known, a lot of drug is being wasted, and a lot of difficulties are the industry, the people are facing a lot of difficulties, right? Like one of difficulties, the clogging of the wires, the space between those wires is like it's filled by the drug, or sometimes the lot of drug is wasted because we don't know how to coat it efficiently. And the reason is because we don't know the fundamentals of this coating process, right? So so whether it's a dip coating or spray coating or curtain coating, in every, at the end, in all coating processes, at the end you have a thin liquid film is flowing over the solid object, right? So that is same for all kind of coating process. At the end you will be having a very thin liquid film flowing over the object, right? So so there are some fundamentals, right? So to understand the physics or to understand the fundamentals, what we did is we took a model problem here where a thin film of liquid is flowing on a patterned rotating cylinder. Okay, so why I'm using word rotating, because in many of the process we rotate the object, right? In many of the coating processes we rotate the object. So we wanted to study how the surface topography or the pattern over the surface or the surface geometry or the object geometry and the rotation of the geometry is going to affect the evolution of the thin film over the object. So that was the objective. Why we are why we choose this? Just to understand the fundamentals. Okay, I mean, the ultimate aim is to do this for the stent and lenses, but to start, right, we I mean, we cannot simply start with this actual problem. So we took a simple problem, and physics is simple, physics is same, sorry, geometry is simple. Okay, so cylinder. So this is when omega is 0. So this R, right? R is R mean plus del sine omega theta. So this R mean is the mean radius. Del is the amplitude of the pattern over the cylinder, right? And omega is the frequency. So this is a shape, or I mean, this is the geometry when either omega is 0 or delta is 0. So in all four cases, I've taken delta equal to 0.05 times the mean radius. Okay, so omega is 0, frequency is 0. This is when omega is 5. This is when omega is 11. This is omega is 21. So what I'm trying to explain here is by changing omega and delta, I can get any of the shape. Okay. So my R is R mean plus del sine omega theta. Delta is the amplitude and omega is the frequency. In all cases, I've taken the amplitude of the pattern is 0.05 times the R mean. Okay, and this is our coordinate system. Okay, so this is, let's say this is the object, and this object is rotating like this. Okay, so this is omega. So the rotating speed is constant, it's omega. Okay, it's not changing with time. And this is the radial coordinate, this is the theta coordinate, and the gravity is acting downward. Okay, so these are the governing equations. So this u, right, the velocity u is the vector u has this radial component w and angular component u. Okay, u is the vector whose radial component is w and angular component is theta, and omega is simply omega times ey. Okay, and this is the momentum equation. So the equations I have written in compact form. Okay, not the individual component form. Acha. So this equation, right? This is this continuity and momentum. These are in a rotating frame of a reference. Not the static frame of reference. Okay, Acha, so why I have why I'm solving equations rotating frame of reference? The reason is, see, this is my object, right, which is rotating in this direction. So this solid, so you have this solid, and on top of this you have fluid, right? So this solid fluid interface, it will be changing it since it's rotating, right? If it is it's a cylinder with no pattern, right? If it is like this, the solid fluid interface will be same, it won't be changing with time. But in this case, this solid boundary changing, this position of the hill is here, and the crest is here. At next instant of time, the position will be different, right? The value have moved to a different value will move to a different position, and hill will move to a different position. So this fluid solid interface is changing with time. Okay, so one way to deal with this is you go for a dynamic mesh. Okay, so here what I have done is I'm using the rotating frame of reference. I'm writing equations in rotating frame of reference. So my frame of reference or my coordinate system is rotating with my object with constant angular speed omega, right? So in that, when you write the equations in rotating frame of reference, you'll get to this fictitious force or to these extra force terms, right? So this one is your centrifugal force term, and this is your Coriolis force term, right? Okay, so this is again, I mean, in the compact form. You can write, or maybe I can write the component form for just one component, and then. But before that, okay. So these are the assumptions. Okay, so since 3D calculations are a little bit difficult to carry out, okay, 2D is, I would say, it's little easy. So we started with a 2D calculation. So we are saying that there is no variation in the axial direction. We are not considering the Z component. And the physical properties like the density, viscosity, everything, it's no, I mean, it's isothermal flow. So okay, they're not changing. They're constant. I mean, the viscosity, density, everything is same. Okay, so the film thickness, right? The mean film thickness or the characteristic film thickness. So it's like this, right? So we have an object. So let's say this is our cylinder, and on the cylinder we have a very thin film of So we have a thin film of liquid on top of this cylinder. Okay, we are not considering any variation in the Z direction, which is inside this the display of your computer or laptop. Okay, so so this is my object. This red one is the cylinder solid object, and the blue one is the film, liquid film. Okay, so this mean film thickness H is very small if I compare it with the radius of the cylinder. So in our problem we have this, right? So we can use this two different length scales, right? So in this formulation I have used lubrication approximation to use this disparity in length scale. So okay, so I'll first talk about the non-inflation, and then we'll go back to the equations. So we have solved. It's a standard practice, right, to solve equation in the non-dimensional form. So the radius r is non-dimensionless by the mean cylinder radius. Okay, the radial coordinate r is non-dimensionless by the mean cylinder radius. Okay, here we have defined a new, so Z is a modified radial coordinate. Okay, so Z equal to 0 means it's a cylinder surface, right? So Z equal to 0, cylinder surface. Z equal to H, free surface. Means the interface of liquid and liquid and air, right? So you have air here, right? So H is the so Z equal to 0 means it's a cylinder surface, Z equal to H means it's free surface, right? So we have used this modified radial coordinate system, so which is R minus R mean plus del sine omega theta. And this H, the film thickness, which is going to be a function of theta and time, right? It is non-dimensionless by the mean film thickness, capital H. Okay, and using this epsilon, we have written h in terms of r and epsilon, so it's epsilon r, right? So this delta, the amplitude of the pattern, it's scaled by the again mean. That means thickness is very small in comparison to the cylinder of the radius. That's why I can say this, we can call it a thin film, right? And the pressure is scaled by rho g h. Okay, this velocity, the angular velocity, okay, is scaled by rho g h square by mu. So rho g h square mu is coming from the flow down an inclined plane actually. So if you so let's say this is your cylinder, right? So this is a cylinder. If you look at locally, right, it is like this. So you have a fluid flowing down a inclined plane. So that's why we are using this the mean velocity for flow down inclined plane to scale our angular velocity. Okay, and this omega, W star, so W is scaled by epsilon times u. So so this, right, the scale for this radial velocity. So we have got this from, so our continuity equation is what? Partial r u by partial r times 1 by r plus partial w partial theta, right? The radial term, I guess, right? So radial term I'm not writing, so I can equal to 0, right? And then so you have to, what you have to do is you have to replace r. So r is what? So we have definition if z is what? R minus capital R m plus del sine of omega theta, right? So this is the definition of z, right? So partial z will be same as partial r, right? And okay, since z is function of r comma theta, right? So if I'm finding this partial by partial theta, I'll have to do like this: partial by partial z times partial z. This is simply chain rule. Z is function of, so I have to find partial theta. So partial z by partial partial z by partial theta plus partial by partial theta times partial theta by partial theta. So I'm simply using chain rule here, right? So so partial theta I have to replace by this, partial r is same as partial z, and then see this continuity equation, right? So both the terms are equally important. So when you do that, right, when you write the non-dimensional form, or when you write u by u star times capital U, right? So u star is a non-dimensional velocity. So you will see as, right. So same thing I've written here. So this is coming, this scale for this W is coming from the continuity equation. Okay. Okay, so this is scaled. I mean, when I use this non-dimensionalization, right? Oh, I forgot to write scale for time. So time is scaled by t equals to t by t star equal to t by u by r. Okay. So these are the different length scales. Okay, when you use that length scale, this is your dimensional form of non-dimensional form of continuity equation, momentum equation. Okay, so in these equations, right, I have written only the I have kept only the leading order terms and the terms which are of first order. Okay, what I mean by saying leading order in the first order. So leading order means the terms where you have simply u, w, something. So it's not multiplied. It's multiplied with 1. First order means it's multiplied with factor epsilon. Second order means it's multiplied with epsilon square. So I have kept only leading order in first order term. So continuity equation, that this is your so this is your left hand side. Right hand side, there are other terms, but those terms are of order epsilon square. Okay, momentum equation. So this is the modified equation or simplified equation. Okay, so again I have taken only leading order and the first order term, right? Okay, this theta plus MWT. So this I have written. I mean, so we are getting this MWT by epsilon square term because we are writing equation in rotating frame of reference. So in dimensional form, it will be theta plus omega t. When you write it, when you non-dimensionalize everything, you'll get this MW by epsilon square term. So this M and W, right? So M is your this is your non-dimensional viscosity. And this is non-dimensional rotating speed. Okay, so so this is our this is the R component and this is the theta component. Okay. Acha. So so there is no R here, so I have converted everything in terms of Z, right? So modified radial coordinate. So Z equal to 0 at the cylinder surface, Z equal to H at the free surface. So we converted this because it's easy to apply the boundary condition, right? It will be easy to apply the boundary condition if I use Z instead of R. Okay, so these are non-dimensional simplified or modified governing equations. So I have not written the full momentum equation or full continuity equation. I have dropped couple of higher order terms. So I have kept only first order and leading order terms. Okay, so one more thing. So in this analysis, right, this M and W has to be of order epsilon. If they are not of order epsilon, then I won't be able to. So I've dropped a couple of the terms, right? So I won't be able to drop those terms. So those terms will be significant, maybe leading order, maybe first order, right? So since I want to keep only leading order and first order terms, so this is the limitation or this is a condition. I mean, M and W, those non-dimensional parameters, has to be of order epsilon. Or I can say that this analysis, whatever the solution I'm going to find, is the cases when M and W both are of order epsilon. Okay. Okay, so these are my modified. So after simplifying or modifying our governing equation, okay. So will be solving those equations using along with these boundary conditions. Okay. Achha, one more thing. Why I have used here, because at the end, maybe you've learned that okay, you're solving full momentum equation. But here in my problem, what I have done is I have simplified my momentum equation. Okay, I have dropped a couple of terms. I've dropped terms which are very small. So I've taken I've non-dimensionalized my all the equations, and then I have done order of magnitude analysis. Like, or I can say, or I would say, I have dropped terms which are small in comparison to the other terms. Okay, so I have terms which I've kept terms which are of order 1. I have terms which are of order epsilon, and I have dropped all the higher order terms. So this is not full momentum equation. This is modified equation or simplified equation. So I'm going to solve that modified equation. And as I said that my equation, the solution, okay, will be valid only when this m and w are of order epsilon. That means my analysis I'm doing it for, as I said W is your non-dimensionless rotating speed. So I would say my analysis is valid only for a slow rotating cylinders. Okay. Okay, so these are the boundary conditions. So at the cylinder surface, we have used standard no slip condition. Okay, at fluid at the free surface, right? At the free surface, so these are the standard boundary conditions. I mean, this first one is your continuity of tangential stress, and this one is continuity of normal stress, right? So this one is like, if this one I get, so this is a simplified form of T dot E dot N. Okay, so E is your rate of deformation tensor. Okay, so it's T dot, okay, okay. So and this one, so this is your tangential stress. Okay, and for the normal stress rise, right? So it's like the jump in stress is balanced by the, so the actual condition says that jump in the stress is balanced by the surface tension. So this one is your the non-dimensional. Okay, I've written all the non-dimensionalized boundary conditions. Okay, so this is, so kappa is your curvature length. Bond number is this rho g r square by sigma. So it's inertia by surface tension force. So surface tension is appearing inside this bond number. Okay, so this whole term is of order 1 by epsilon. Okay, so this is, I mean, these are the is another boundary condition at the free surface. Okay, so it's called kinematic boundary conditions, or you can say the normal velocity is, the normal fluid velocity is same as the free surface velocity, right? So this is the mathematical form of kinematic boundary condition. These are all standard boundary conditions. So at fluid-fluid interface, we have continuity of velocity, continuity of stresses. At fluid-solid interface, you have no-slip condition. Mostly we use no-slip condition, right? But I mean, there is a question on the I mean, there are some discussion going on the validity of no slip condition, but he can, at least for our calculation, we are using no slip condition. And so no slip condition, continuity of tangential stress boundary condition and the kinematic boundary condition. These are the standard condition which I have used here. So we will be solving those simplified modified equations along with these boundary conditions. Okay. So in lubrication approximation, right, or it's also called long wave theory. So in my equation, right, in our equation, you can see we have this epsilon, right, the small quantity. So when you have this when you have this small quantity, right, epsilon in your equation, this is like one way of getting solution. So you expand, so your unknowns are u, v, sorry, v, u, w, and p, right? So I can write u as u0 plus epsilon u1 plus epsilon u2 plus epsilon square u2 plus epsilon cube u3, like that. So that this is an infinite series. Similarly, I can write for w and p. Okay. Acha. There is one small change for p here. So u and w have written u0 plus epsilon u1 plus epsilon square u2 plus other terms, w0 plus epsilon w1 plus second order plus third order terms. But in case of pressure, I have written epsilon inverse times p0 plus epsilon p1. So this is why I have written this, because in this lubrication problem, right, I know that pressure varies with 1 over epsilon. So that's why I've written the first term is epsilon inverse times p0. Okay, so what we have to do is we have to replace u and w and p by these expression in our governing equations. Okay, so what what I'll do, all the components, it will take very long time. Okay, so the original continuity equation is what? Partial r u by partial r 1 by r plus 1 by r partial w by partial theta equal to 0, right? So if I write this in terms of z and non-dimensional parameters or non-dimensional r, u, and w, and then it will be like this: partial by partial z, okay, plus partial u by partial theta. See, I mean, there will be some extra term because my z is function of r and theta, so it will be partial w theta oh sorry, it has to be w and u. So it's w plus partial z times delta omega. Okay, so there is omega and there is w. So omega is the frequency of the pattern and w is the radial velocity. Cos of theta prime equal to 0. Theta prime is omega theta. So this is dimensional one, I guess. And okay. So when you replace w equal to w0 plus epsilon 1, order, take the leading order terms only, then you'll get this form. The continuity equation will be partial w partial z plus partial u0 plus partial theta minus partial u0 by partial z times del w cos of theta, right? So this is the leading order equation. Okay, and similarly the this is continuity equation. R component is minus of So R component means I'll be keeping only the leading order terms. So I'll drop all the terms which is multiplied with epsilon or epsilon square. Anyway, I mean in my equation I've kept only the terms which are multiplied with epsilon only, not epsilon square. So it will be R component is going to look like this: minus partial P0 plus pi partial Z minus sine of theta equal to minus of W square. So sorry, these are the dimensional non-infinite equation. Theta is partial square U0 by partial Z square minus of cos of theta equal to 0. And the boundary conditions are, so if I write the leading order term, partial u by 0 partial z equal to 0 at z equal to h, and q equal to 0 at z equal to 0, that is no slip condition, and w equal to 0 and p0 by the from the normal stress condition I can write p0 equal to b0 h plus h theta theta plus del, let's write like this, partial square h by partial theta square plus del of sine theta prime minus del omega square sine theta prime, right? So this is the condition at the it is z equal to h. Okay, so when you solve this, right, you will get your leading order solution. So it's not difficult to solve. So you can find u0, you can find w0, right? You can get expression for u. Okay, so this is p0 at z equal to h only. So by solving equations, continuity and momentum equation, you can find u0, w0 and p0, right? Similarly, you can find u1. So next is like you can write the terms or equate the terms which are of order 1, like which are of order epsilon, and then same thing you have to do, same thing you have to write the r component, theta component, continuity equation and the boundary condition, and then you can solve for u1, right? W1 is not required. Okay, so once you get u1 and w1, you can use, okay, so okay, just show this. So so you got your u0, w0, w1. So w1 is not required, u0. So leading order and first order correction for u. So the kinematic boundary condition, the condition at z equal to h, which is nothing but the normal fluid velocity is same as the surface velocity. When you simplify that, when you use that u0, u1 and w1 there, you will get your evolution equation, which is a fourth order differential equation. So this is our evolution equation. Okay, so I got this evolution equation when I put my u0, w0, w1 in my kinematic boundary condition. Okay, so this is a fourth order differential equation. Okay, so the second term here, this one, the terms which I have written in the green term, right, letter in green color, these are like coming, or these are appearing because of the surface topography. Or let's say if I don't have any pattern over the surface, let's say it's a smooth cylinder, it will contain only this, the first line, partial h by partial t will be this much only. Okay, all these terms will be gone. Okay, so these are the terms which are appearing in my evolution equation because of the geometry of the, or because of the surface topography. Okay, so solution of this equation, I mean, we have simply used a semi-implicit method. So first, I mean, we discretize the equation using finite difference method, and we have used finite simply semi-implicit method. So semi-implicit means only so this fourth order term, right? This fourth order term is handled implicitly, and all the other terms are handled in explicit way. Okay, so that's why it's semi-implicit. Okay. So before going to this to the actual problem, what we have done is we have validated our code. I mean, you have a cylinder of radius r, a static drop which is hanging below the cylinder. So I can get analytical solution for this problem by just doing force balance. Okay, so we got the surface by doing force balance, and then we compared those results with the numerical results, and also this thin film flow over a smooth rotating cylinder. So the results are available for thin film flow over a cylinder, smooth cylinder, where there is no surface topography. Okay, so we have results for that. So we have compared our results with their, I mean, the results present in the literature, and they were matching very well. So we, after the validation process, we ran simulation to get results or to see the effect of surface rotation as well as the surface topography on the evaluation of the film. Okay, so these are some results. Okay, so the initial condition for this is like this. So so we started with, so we have this solid object, and we initially started with a, sorry for this drawing thing, but uniform fill. Okay, h equal to constant, initial condition. So initially you have a uniform film or the film of a constant thickness over the cylinder. Okay, so first I'm presenting results for the rapid spinning. Okay, rapid spinning means, okay, I mean in our calculation we have dropped this gravity term, or I mean we have scaled, we have done scaling. We've rescaled our velocity and velocity basically, and time actually, and then okay, so the results are already present. So Evans in 2014 they published this in Physics of Fluids. So what they have presented is, so when you start with a continuous film around the cylinder, and when you rotate it at high speed, right, there is instability occurs, and this thin film converts into drops, and these drops are connected with very thin film. Okay, so in this simulation you can see I have put an GIF image here. So we started with a uniform film around the cylinder. Okay, and this S is the Weber number, and which is rho omega square r cubed by sigma. Okay, so we change the scaling here, right? That's why we are able to show the results. Otherwise, with the original scaling, our analysis was valid only when m and w are of order epsilon. But here this is more than epsilon. Okay, so. Evans they did stability analysis. I guess one of the faculty from IT Roper, he is going to discuss this stability analysis in the next session. So so they did stability analysis, and they showed that this continuous film breaks into number of drops, and then the number is equal to square root of s plus 1. S is this Weber number, which is rho omega square r cube by sigma. So from our simulation, we're able to show that we're able to match the number of drops. So we started with continuous film, and then we can see we have 1, 2, 3, 4, 5, 6, 7. So square root of 1 plus 100 plus 1101 by 2 is 7, 6 point something. So the perfect integer is 7. So we got, so we started with a uniform film or film of a constant thickness around the cylinder, and then at the end we got this kind of profile. So okay, these places, right, 1, 2, 3, these locations, the film profile or film thickness is not 0. They are connected with very thin film. Okay, so the why I'm saying it's not 0, because we don't have those forces, right, in our formulation. So if you want to capture this rupture or those things, you'll have to add the intermolecular forces. Okay, so here we don't have those forces in the formulation, right? So okay, in case of pattern cylinder, right, what we found is, so it's not function of S. So irrespective of S, it's equal to the number of the frequency of the pattern. So it's omega is 11 here. So we started with a film of a constant thickness, but the end, what you're seeing here, what we are seeing is all the fluid is getting accumulated over the valleys. So these are the valleys. So these are the hills. So it has, the fluid has accumulated over the valleys, right? So in case of smooth cylinder, the number of drop depends upon your that non-uniform parameter S. But in case of pattern cylinder, it is controlled by the surface pattern. Okay, but S has, I mean, it's not like it doesn't matter what is the value of S. So this is when S is 30, and when we increase the number of S, we saw that okay, it's not same as the number of valleys or number of hills. So it's like, and also the drop is not forming exactly on the hills, on the valleys. It's forming somewhere else in between, and the number is not same as the omega. But when we go for a slightly higher value of S, so here S is 80, right? So here the drops are forming on the hills. You can see we started with a uniform fill, but here it's starting on, it's forming over the, so hills here, 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 and again the number of drops are same as the omega. Okay, so in low value of S, the drops were forming over the valleys, and high value of S, it's forming over the hills or crest. Okay. Okay. So, and again, I mean, this is like we can keep running. So this is the profile at time equal to 4, whatever. But this is after some time it reaches to steady state. It doesn't change with time. Okay, it's not like the number is going to change, or the drops going to stay there only. Okay. Once it reaches to steady state. Okay. Now, okay, I can skip this part. Okay. Now, coming to the case when the gravity is important. So in the last few slides, the gravity was weak, or I could say it was, the cylinder was spinning at a very high speed. Okay, so but when the gravity is important, right, it's comparable, okay, and to centrifugal force, then okay. So in case of smooth cylinder, right, we have seen that okay, I didn't show you the profile, but in case of smooth cylinder, it reaches to steady state. I mean, you started with a uniform fill, and at the after some time we get a bulge or drop like shape at the lowest point here, right? So but in case of pattern cylinder, right, because of the surface topography, it never reaches to steady state. You can see this bulge is oscillating, Okay, in case of smooth cylinder, so you start with a uniform film and then this kind of a bulge at the lowest point here. Okay, Acha, the initial condition, right? We have tried with different initial condition. I mean, so in case of pattern cylinder, we have tried a film of constant radius as well as film of constant thickness. But at the end, we get same result. So it doesn't matter what is the initial condition. Okay, so unlike smooth cylinder, in case of pattern cylinder or when the cylinder has some pattern over the surface, the film thickness never reaches to the steady state. This bulge is going to oscillate with time. Okay. So this is for bond number 100 and W equal to 2 × 10⁻³ and M equal to 7 × 10⁻³, right? So so if I increase, so bond number I have, okay. So this is for bond number 100, right? If I run it for bond number 10 or 1, this bulge, right? The size of the bulge will be smaller. Okay, because smaller bond number means I'm going for the higher surface tension force. So the surface tension will oppose the draining motion, right? So that's why the size of the bulge will be smaller if when I go for a smaller bond number. Okay, so okay, here I'm showing the speed, the effect of speed. So when so this is at lower rotating speed, which is 0.002. This is at 0.016. Okay, so that was 2 × 10⁻⁶. This is around 1 × 10⁻². Okay, the viscosity is, the non-dimensional viscosity is same. Okay, one thing about this non-dimensional viscosity, so whether I'm going for M to 7 × 10⁻³ or 1 × 10⁻³, whatever, it doesn't matter what is the value of M. It has to be small, but once it is small, right, it doesn't matter whether it's a 7 × 10⁻³ or 1 × 10⁻³. It is not affecting the final profile. It is affecting the time to reach steady state, but it's not affecting the final profile. Okay, and when you increase the drop size, the rotating speed, right? So this is W to 1 × 10⁻². So you can see, I mean, the cylinder is rotating at high speed, right? So more liquid is rotating with the cylinder. So there is no bulge forming here. Most of the liquid is rotating with the cylinder. Okay. So at lower speed, you'll get a bulge at lowest point, which is oscillating. At high speed, it is most of the liquid is going to rotate with the cylinder. Okay, next here I'm going to show you, so in the formulation I haven't added this intermolecular force part, but when I add it, right, so I'm able to capture the film rupture. Okay, so here when this is for bond number 1.1, A is your non-dimensional Hamakar constant. So I have added a potential term in my governing equation. So with pressure, I have added term phi, which is A by H cube. Okay, so along with pressure, I have added a potential term there. So phi, I have added a phi, which is A by H cube. Okay. So this is our intermolecular force term, which I have added in our governing equation. Okay, so when A is 0 means, I mean, there is no intermolecular force. So you'll see you'll get this kind of film profile. So we started with uniform film of a constant thickness around the cylinder, and then we got this kind of bulge. Right? This is at bond number 0.1. And when I add this intermolecular force term, so this A is 1 × 10⁻⁸. So A has to be of order, I mean, see, it's a phi equal to A by H cube, right? So A has to be of order H raised to 3. Then only that term will be of order 1, right? So that's why H is very small here. So you can see, okay. so in this image one, this image, there is no rupture. In this image, you'll see the film is almost touching to the cylinder at these locations. So those locations, right, that this interval force term become dominant. So it ruptures where the film ruptures where the film thickness is minimum. So if I talk in terms of force, in that portion, that force will be dominant, this interval force, because it's A by H cube. Where is with A by H cube? So that force will dominate, and the film will rupture at those locations. So in this, it's not changing with time. But if you run it for, if I run it, so after this, right, I get negative thickness. That means this is a rupture time for this bond number and this value of A. If I increase the, okay, so this is for higher, no, this is for this W, okay. Okay, this is okay. So this is for pattern cylinder. Okay, this first one is when that there is no intermolecular force, so it will be simply oscillating with time, right? They won't, you will not be able to capture the film rupture, right? But when you add it into a force, see, it's rupturing at these, film is getting ruptured at these two locations. Okay. This is okay. So this is stationary cylinder actually, and this is a rotating one. That's why I kept this. So, but there is no intermodal force term here. Okay, so this is what we have done using our. I mean, this is like, I would say this is the like theoretical. I mean, though it's not completely theoretical because I'm not getting analytical solution, but okay, I have simplified my momentum equation and then I've solved, numerically solved it simply. So I've derived an evolution equation, like I've derived a differential equation to get my H, which is function of theta and time, film thickness. Okay. Next approach is like, let's say I say CFD modeling, right? So, okay. So here in VOF method, so I have used, okay. So, okay. So in this part, right, we are solving full momentum equation. Okay, we're solving for U and W, right? And using U and W, we are predicting this interface. So you have this solid, you have this part is liquid and this part is air, right? So so we are calculation here, right? So we are using this VOF formulation, right? So in VOF also we are using the CSF model, continuum surface force model. So surface tension is appearing in my governing equation, in my momentum equation, as a force. Okay, so and then this interface, right? I mean, the interface is the tracking of the interface is done by the a parameter alpha, volume fraction, marker, you can say marker point. So we have right. So so in VOF method, right? So let's say this is a container, and this is, let's say, air, and this is liquid, right? So basically, let's say these are the cells. Okay. working. Sorry, this is not working. So in volume of fluid method, right, we track interface. So this track or tracker, or we track the interface using the parameter called alpha. So alpha is our volume fraction actually. So in a given cell, we calculate alpha. So if alpha is 0, that means, let's say we have two phases, liquid and air, right? So when alpha is 0, that means, let's say it's air. Alpha is 1, that means, let's say it's liquid. So for in our computational mess, right, if that cell is filled with liquid, it will be alpha will be 1. If the cell is filled with air, the alpha will be 0. So depending upon the alpha value, and if alpha is in between 0 to 1, that means that cell contains the interface, right? So in UF method, what we do is we have our momentum equation, right? Along with momentum equation, we solve the equation for alpha, which is advection equation for alpha. Okay, so that basically tells you how the interface is moving or how interface is changing. So along with momentum equation, we solve one more set of equation for alpha. Okay, so you get your UV value and then you get your alpha. And for the next time step, using alpha, you calculate the properties. So because let's say if alpha is 1, it will be simply a liquid. Mu, it will viscosity will be same as a liquid velocity, right? Density will be same as a liquid density. If alpha is 0, the mu will be same as mu will be the air viscosity and density will be the air density. But alpha is, let's say, in between, then you have to find the property of the fluid depending upon that alpha. Okay, and based on that alpha, you have to draw the interface also. You have to construct your interface. So for constructing interface, we have different methods available. So like one of them is piecewise linear interpolation, something. So we have, so Plick is like in this case of problems, Plick gives you more accurate interface. Okay, so I guess in Fluent we have Plick is there. So in our calculation we use this Plick. So in VOF you have to solve momentum equations and then one more set of equation for alpha. Alpha is your volume fraction, right? So the equation for alpha equation. Okay, alpha and it will help you to draw the interface. Okay, so the same problem we have solved using a VF also. Okay, so this we have done using ANSYS. Okay, so we have so we have taken a square domain. So it's like we have taken so we have taken a square domain and this is our solid, right? And this is here we have done mesh here, right? Okay, and then around this cylinder, right, initially we patch, so we make a thin layer of liquid, so we patch that part by our liquid. Okay, and then we solve this our momentum equation and the equation for alpha. Okay, so this is the case when the bond number 100. So we are able, so this blue triangles, filled blue triangles, these are the results presented by the bank of. They have used, I mean, they use lubrication approximation, and this is a film profile. Okay, so again, they started with a uniform film, and this is the final steady state profile. Okay, so this red dot or red line is the results from the VOF method. So they're matching very well. Okay, this is for stationary cylinder, W equal to 0, and this is for the moving cylinder. Okay, in both the cases we are able to match their results. So our calculation is when we are solving full momentum equation, there is they have predicted the interface thickness by. So why we have moved to VOF? Because okay, we can get the solution using the lubrication approximation, right? I mean, it takes less time. I mean, if I compare it with VOF method, but in case of pattern cylinder, right? Okay. Okay, so in case of pattern cylinder, we have seen that if the pattern amplitude and the frequency, if pattern amplitude is significant, so all the results I have presented is when the amplitude is 0.01 times the mean radius, right? So let's say if I want to go for 0.1 or 0.1 times or 0.1 time R, then you can see start. I mean, we have seen that it starts, the lubrication approximation starts to fail, because there is another length scale appears when you go for a delta 0.1 times R or the higher value of delta. So there the lubrication approximation starts to fail. So if you want to capture the interface, right, you will have to go for the solution of full momentum equation. Approximation doesn't work there. So that's why we wanted to do the same thing using VF, so that we can get the solution, or we can get the profile for the pattern cylinder where the amplitude of pattern is significant. Okay, because all the results which I have presented before, the amplitude of the pattern is not significant. It's 0.01 times R. Okay, here I'm showing you. Okay, so we did using VOF, we did couple of numerical experiments. So here what we are trying to do is we for a given film thickness, right, for a given initial film thickness, we wanted to find how much rotation is required to support that initial film, right? So you can see here this when the rotating speed is 0.01. Okay, so 0.01 is bit low. I mean, it's not able to support that film. So there is a draining of the film, right? So in case of thin film, we have seen that it drains, but at the end you get a bulge kind of shape at the lowest point, right? But when you increase the film, right, you are increasing the weight of the liquid. So some of the liquid is going to come out of this solid object. So, and here we are rotating, but still this rotation is not sufficient to support that liquid. And when we went from W equal to 0.01 to 100, we can see that it is splashing. I mean, because of the higher central force, the liquid is leaving cylinder. But when, and this is the shape, this is a profile for W equal to 1. So I can say that when W equal to 1 for this film thickness, W equal to 1, we are able to support. If I go from, so I'll have to do a couple of, again, runs, different simulations to get the speed. I mean, I can do a couple of more numerical experiments to get a desired. I mean, let's say I want to get a uniform film around the cylinder. So I can by doing numerical experiments, I can find the specific speed. So this is what we wanted to do. I mean, how much rotation is required to support the given film thickness. but still you need to run multiple simulation. And since we are using explicit approach in VF, you can use explicit approach only. So the time step has to be very small. So that is one kind of limitation here. Okay, so yeah. Okay, so I'll conclude my talk. So these are the like conclusions. So we have studied the effect of surface topography and surface rotation over the film, 2D film evaluation around the cylinder. And when the cylinder is rotating at very high speed, your film converts into drops. Those drops are connected to very thin film. Okay, so in case of smooth cylinder, it's the number of drops are simply function of your rotating speed. In case of cylinder, it is controlled by the surface pattern also. So at low speed, we have seen that it's same. So at low and high speed, we have seen that it's same as the frequency of the pattern omega. But in between there is something happening. I mean, there's some instability happening, and it's not same as the omega. And at low speed we have seen that it's forming over the valleys, over the troughs, but at high speed it's forming over the hills or the crest. Okay, so I can say that it's the film is very sensitive. The film profile around this object is very sensitive to the surface topography. Okay, so these are like, I mean, we can extend this work, so we can do it for the 3D calculation. We can do 3D calculation, and since most of the processing liquids, they don't follow this Newton's law of viscosity, so we can add non-Newton rheology. And in case of lubrication approximation, we haven't included initial effect. So, but VF, yeah, I can say in VF we have added all the effects. Mass transfer effects we can add, because most of the coatings, I mean, initially if you leave it for some time, some evaporation also. Profile we need to include the evaporation also, and then later on, I mean, since we are doing, we started with very simple, but to get the actual one, we need to, I mean, you can extend this for a complicated geometry like extent or length I said. Okay, so I guess I'm done with my presentation. I would be happy if you have any. I would be happy to answer if you have any question.